All right, let's do this. Welcome to another stream. Today, let's start. Let's start immediately. I have no time to lose. First thing is the continuation of the deep learning that I've been doing last time I stopped. So let me just find it. All right. Where's my tablet? Here. All right. So I also have my tablet here. And okay, if I'm not mistaken, the last time we stopped was we talked about code. Or to be more clear, let me just open the Visual Studio. It's here. All right, we stopped here last time. So what happened here is we wrote some code. I wrote some code that plots the function that we have and its derivative. So before I even continue, let's make sense out of it. So let's start all the way from the start. Basic functions. So these are the two functions that we are using. We are using the square function and the leaky rel u. I have no idea what this does. Let me just so square and leaky rel u, or the full name of it is a rectified linear unit activation function. It's used commonly in machine learning and deep learning, and particularly in neural networks. Do I have a typo here? I do. So can I run all now? Okay. Okay. Next thing, we actually computed the derivative. So if I just come back here and I show you the derivative calculates the rate of change. Let me just turn this off. So it calculates the rate of change, and basically here on the right you can see a graph of it. So we have a point A and we have the function at A, and then we find a small point before and after A, and we calculate the function of this of these points, and at this point we connect these three dots and we get the slope. Why is this useful? No idea. So let me just open this back again. So this function is actually calculating the numerical derivative of a function fx. So this is the function. I'm providing the function as a parameter. It's a callable one, so this means it's a function. It takes an array, returns another array. We have an input which is an array. We have a delta, which is a small value which represents the step size for the difference approximation. And the core logic, once again, I'll show you, is here. That's it. So, sorry, not this one. It's this one. So basically what this does, it approximates the slope of a function fx at x. So, and that's it basically. I think it's a technique used for estimating the derivative of a function by evaluating the function at two nearby points. And how it works? So let's open this again. So here, this is the way how we measure change in a function over a small interval, and dividing this, this is actually the way how we calculate this change, and dividing it by this, we give an approximation of the slope at x. All right. What is the next thing here in the code? We imported the list. We create two types, I think, the array function type and the chain type. And here we have chain length 2. We have a chain as an input. We have an ND array. We return an ND array. Okay, this is an assertion. Okay, so this basically this is simple. We just have a list of array functions, and I'm getting the first one, I'm getting the second one, and I'm setting them to be equal to these two variable names, f1 and f2, and then I'm just calling x on both of these. All right, now we also have the sigmoid method. So just do this. So what we have? We have the sigmoid function, which implements this a mathematical function, machine learning. So this is how this function is defined. Let me just close this. One plus a minus x squared. E is the base of the natural logarithm. It's around 2.718. So this sigmoid function will take any real number x as an input, and it will transform it as a value between 0 and 1. So I think that in this case fx will go to 0 as x approaches minus infinity. And basically I think we can test this. Basically it's, let me just say, it's 1 over 1 plus, so if x, let's say if x is minus 10, let me just open my calculator. So Let me search for, okay, so I have the calculator, so I want to see E, where is squared? E minus 5, but because it's already a minus, so we're gonna put minus 5. So what's this? All right, this is 1 plus 148, so it's 1 point something, so it's a long number. It's 1 divided by 149. How much is this? 1 divided by 149, it's around 0.0067. all right, let me just get my phone. I think I'm gonna do this faster on the phone if I just turn on the calculator. Where are you? Here. So if x is minus 1000, so what we will have then, we will have E minus 1000 okay, so my calculator is actually saying me that it doesn't work for 1000. Maybe let me try. Let's try with 50. Okay, so with 50 it's a really big number. Wait, so I didn't do something right. Because my phone calculator is giving me a different answer than my. Let me clear this. Okay, so it gave me a different number, but basically I want to clear this. My point still stands. As we increase x, as x actually goes, not as we decrease x, the function is gonna approach 0, but if x approaches plus infinity, the function will be 1. So basically the sigmoid function maps positive or negative inputs into values ranging from 0 to 1. All right. And if we had an array, let me just do this as well. I'm going to delete this. So if I had a NumPy array consisting of -2, -1, 0, 1, 2, what will we get if we print this? We're gonna get values like 0.119 with more numbers after this, 0.2689, 0.540, 0.73, 0.88, and so on. Right. Alrighty, so let's go back. What? Oh, my stream was private the whole time. Maybe that was good. All right. Now we're live officially. Okay, so we are also chaining our derivatives here. This is just a helper function that plots, another helper function that plots as well. Okay, what if I want to do the following? Instead of chaining it, I just want to chain one. What if I just want to have a square function here? Will this work? No, it won't. Why? Because I have an error on line 39. That's AX. Ah, this is AX. So, so wait, I'm only looking at this chain here. Chain one, plot chain derivative. Yes, this is all I want. Why doesn't it let me here? There's an assertion error. Length of input chain should be 2. Ah, okay, so what cell is this? Length of chain length 2. So where is the chain length 2 method? Ah, plot chain. So I assume it's here somewhere. Yeah, it's here. Wait, so can this be like this? Okay, I don't need to do this. I can do sigmoid here. Will this work? Wait, it's not x. What's the value of this? It's chain 0 input range. Chain 0, and I'm gonna take input range here. All right, so okay, so here I have the function and the derivative for only the square of x. So I removed the sigmoid completely out of the equation here. So I'm just trying to visualize it in order to build intuitive understanding. So the orange line, again, it's a derivative f prime of x, which represents the slope of the tangent line of the graph of f of x at any point of x. So this actually is giving me the steepness. So if x is greater than 0, so we are taking these points into equation, starting from 0 all the way to the right. So if x is greater than 0, so f prime x will be so this will be also greater than 0, right? And at x 0, it's exactly 0 here as well. Can I increase this? Can I increase the range? Let's, instead of -3, let's put -10. 10, and I don't need to increase it by 0.01. I can increase it by 0.5. So it's more or less a straight line. Right, let me just increase this. -5, 5, run. -5, 5, 0.1. No, 0.1. Let's put it like this. Let's maybe use -3 and 3. So let's do a test. Let me think about this. So I'll remove this. So at point I don't know, let's say 2. I think 2 is a good point. So what I'll do is I'm gonna pick a point on the graph of f of x is x squared, and I'm gonna need to draw the tangent line at this point. So what happens? So what if I have f prime of 2 as 4? Maybe not use 4 because let's use 3. So I have f of x is x squared, f prime of 3 is 6. So what does this mean? At point x equals 3, the slope is f prime of 3 6. So which means that the tangent line will rise 6 units for every unit that it's moved horizontally. Wait, let me think about this again. Let me do some soul searching. Let me do some introspection here. So what do I have here? Wait, let's do this again. So let's plot
let's do it step by step. So let's plot f of x, which is x squared. So I'm gonna imagine it's something like this and like this. Well, let's say this is symmetric. And now let's plot f of 2x, so which is a straight line passing through the origin with positive slope. Two, 4, 6, 8, 10. So if I have 1, it's 2. If I have 2, it's 4. If I have this, it's this. So it would be like, but how does this make any sense? All right, so I have these derivatives. I know what a derivative is. So it's like asking how steep is this line, or I don't know, how fast is something moving, or it's like asking yourself, if you are in a car, it's asking yourself how fast your position is changing as time passes, as time moves on. Now, let's say I'm walking. Oops. So I'm trying to explain this to me to understand better. So I'm walking, and sometimes I walk fast, sometimes I walk slow, and sometimes I stop. And if we track where we are at every point here, we can measure how fast, how our position changes over time. So if I say, if I move 1 point every second, I'm walking at a steady pace. If I suddenly take 1, 2, 3 points, I'm going faster. And if I stop right here, my movement is 0. So a derivative is just a tool that calculates this change. It measures how our position changes as the time goes. So how does this work in a relation to a graph, because that's where so I have x and epsilon axis. I have time, so this can be time, and this can be position. And if we plot our position over time, so if we plot our position over time, it can be a line if we are working at a constant speed. So 1 is a 1, the second I have 2, the third second I have 4, blah 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 blah. All right. But if we are speeding, maybe the first time we did it okay. The second step was also done in a second, but maybe in the third second we moved, instead of, I don't know, 1 meter, we moved 5 meters. So it's gonna be higher here on the line. And then suddenly, if the next second we moved, I don't know, only half a meter, so it's gonna be this, and we can plot this like this. So we have the slope here on the graph, and the slope of the graph, it is telling us our speed. So if the slope is steep, like here, we are moving fast. If the slope is falling, we are moving slow, but also there is an option to not move at all. So for example, if we don't do anything in the next couple of seconds, 0, so it's gonna be like this. I don't know if you can see this. So this, and this. All right, and now we can actually use a real example. We can use x squared. So at x equals 2, the function is 4. So the graph at this point, I'm going to just create a simple small method. It's 2, 2. So graph at this point is here. It's 2. So the point is 2, 4. Now, how steep will this be? So in this case, we can zoom this a bit, and this is the part that's zoomed. This is the point 2, 4, and I can pick a tiny change in x, like going from 2 to 2.001. So it's gonna be somewhere. So if this is 2, let's say this is 2.001, it's here. So I'm calculating the f of x is x squared of 2.001. It's gonna be 4.004001. Let's say it's here. So next I need to calculate how much epsilon is changing, and I'm gonna do this by dividing 4001 minus 4. It's gonna be 0.004001. And x is changing by how much? It's 2.001 minus 2. It's 0.01. 0.001. All right. And then the slope is this divided by this, and that is, I think, 4. So the derivative at x equals 2 at this point here is 4. So what does this mean? It means at x equals 2, the graph is climbing upwards at a rate of 4 units for every 1 unit of x. So it's x equals 2, so the derivative is 4. All right, so that's it. That's it when it comes to derivatives. Let me just remove all of this, because this was just testing stuff. Okay. And let me also here in the code revert this. Where have I? All right. So basically, the same thing can be applied here. Let's say at x equals 1, I have this here, and looking at the derivative, I can see, oh, okay, so the x is growing. The function is growing as x is increasing, and here the function is not growing so much because it's more or less flat. That's why the derivative is flat as well. Interesting.
So let me reiterate this for myself. So when the functions are going upwards, the derivative is also positive. And when the functions are flat, like here more or less on the edges, the derivative is 0, like here and here. And when they are downward facing, the derivative goes to the minus value. So what actually did here is that we computed mathematically, and also we graphed the derivatives of composite functions. And it says here, deep learning models are mathematically long chains of mostly differentiable functions. All right, now I'm gonna do another example. So just a second. So and we just need to find differentiable functions, and differentiable means, let me just write this because I'm also gonna forget this. Differentiable able to compute its derivative at every point. All right. Okay, now let's do another example. Another example. Let me turn this on again. So I'm gonna create an even longer chain. Let's say I have 3 differentiable functions, f1, f2, and f3 here. And I want to compute the derivative of f1, f2, and f3. How would you compute the derivative? So judging by what I did just a moment ago, I should be able to do this, because if composite functions composite is made by differentiable functions. So the composite should be differentiable as well. All right, so mathematically, this should look as following. So right, so this is mathematically the following expression. So the derivative of this complete expression is the derivative of calling first the function 1 on x, then calling f2 on x, then the derivative of f2 times calling the f2 calling function f1 and x, and then this last derivative. So how is this working? How is this working? Oops. All right. So let me just think about this for a second. Um, so what is happening here and why is it happening? So all right, so I want to compute the derivative of composition of three functions, f1, f2, and f3. And they are written as f3 is calling f2, which is calling f1, and f1 is taking x as a parameter. So I'm starting with x as an input. F1 is calling x, which will it's processing x, which will produce f1 of x. Then f2 will process f1 of x, which will produce this method, and lastly f3 will process this. So we want to know how this changes with respect to x. So and how we can do this is by using the chain rule. We use it to differentiate composition of functions. And how we can do this? We can do this by using this function that I wrote here. So what I want to start at the othermost function, and I'm going to take its derivative at the point f2 f1 of x, which is then being called by f2 of x. Then I'm multiplying this by the derivative of f2, which is evaluated at f1 of x, and then I'm multiplying it by the derivative of f1 evaluated at only x. So what happens and why is this working? So if we change x, this guy, only a little bit, it will change f1 of x by a certain amount, and this small change then causes a change in f2 f1 of x, and this change causes a change in f3 f2 f1 of x. So the chain rule is combining all of these small changes at each stage to compute the overall change in the output with respect to x. All right. Let's create a diagram here. So I have f1, f2, and f3, and I'm producing 5 as an input. And I'm getting an epsilon here, but in every mid step we're going to have here f1 of x, and here we're going to have f2 f1 of x. So what is this meaning? This means that this derivative is depending on 5, and this one is depending on the result of f1 of x, and epsilon is depending on this. All right, so another intuition is saying the following. If we imagine the input to the composition of these methods being connected to the output, so if this is the input and this is the output, by a string, then if we change the input by a small amount, the derivative will change by f1 prime of x, which will then result to having changed to this, and so on for the third step. Okay. All right. Nice. So 1 hour of this deep learning. Let me just take a small break, and I'm gonna continue because I need to do something else as well. I need to do something else as well here. Okay, see you in a while. Okay, so what happened there? That what happened was I was talking the whole time, but my mic was off. So basically, what I started here, I didn't do much. I am learning. Actually, I'm trying to teach myself possible skills for interviews in the future. So one of the things I want to learn is the hash table, and I created a mind map of the hash table so I can remember it better. I usually do remember better when I use mind maps. Basically, a hash table is just a data structure mapping keys to values. How to create it is an array of linked lists and hash code functions. This part down is a visual example of how a hash table could look like. And here it says how we might use it, how we might insert a key. Basically, we are computing the keys. This is the key. Hi is the key. We are computing the hash code of hi, and it will usually be, oops, okay, I can also zoom in. I'm gonna use this, which can be an integer number. And as you've seen here with AAA and BBB, we can even have same hash codes. Then we map the hash code to an index in the array, and we can use any number of hashing methods, or we can even just do hash of key divided by modulo of array length. And of course, we can map to the same index as we mapped here. So at this index, we have a linked list of keys and values, and we can store the key and the value in this index. And why are we using a linked list? Because of collisions, we can have different keys with the same hash code or two different hash codes that map to the same index. So how we can retrieve this is if we are searching, for example, for the value of AA, so we compute the hash code from the key, and then we are looking for the index from the hash code. And then we search through the linked list for the value with this key. So if we have a lot of collisions, like we have here, the worst case scenario is O of n, where n is the number of keys. But if a good implementation is implemented, the lookup time is O1. Lookup time O1. Worst case runtime is O of n. All right, so Okay, so as I said, a hash table is a data structure that's storing key value pairs. Keys are mapped to values using a hash function. Now, it allows for a very fast data retrieval, and as I said, it's typically O1 for both lookups and insertion in average cases. So once again, a key concept. We take a key and we convert it into an integer, and the integer is used as the index in an array. And we can convert, as I said, here's an example. I can convert foo to 456, which maps to index 0, and here is foo found. And this integer index will determine where the key value pair is stored in the hash table. And a hash table uses an array to store data, and the hash function calculates an index in the array to place the value. And you know, because of the collisions, because different keys can produce the same hash index, hash tables use methods to handle collision. We can either chain, as we did, or we can store multiple key value pairs at the same index, or we can find another available slot in the array. So let's do this. Let's try an example of this. Okay. Python. What can I do? Hash table py source env bin activate. All right. So now when hash table. All right. So what I'm gonna do is I'm gonna create a class called hash table. And let's think about what I need to implement this. I can either do linked lists or all right. So let me just turn this on. So let's implement a hash table that uses actually, oh no, why is this suddenly so small? Let me just center my tablet. Is it here? It is here. Okay, so let's implement it. We're gonna have an array which is gonna serve as the primary storage, and we will have a linked list which will be used to handle collisions. So what I'm gonna need is implementation. So what I'll have is a node class, which is going to be the primary working unit of the linked list, and a hash table that's going to manage everything. All right, so let's start with just going to close this. Let's start with the node. So not the hash table. but the node, I need to initialize it, so I have a key and a value. So the key is the key, the value is the value, and the next is none. So this is the pointer to the next node. So for those of you who don't know, linked lists are actually implemented using nodes. Nodes are elements that have keys and values, and also can contain a pointer to the next node. So I can also have here a class called the hash table, and let's initialize. So what does the hash table do? What I need to provide for the hash table? Initially, I need an array, right? I need self, and I need a size. And let's say the size is 10. I can put here self size equal to size, self table is equal to none times 10, so times size, because we're gonna have the size of the array will be the size that we provide here. Okay, next, hash function. So I'm providing a key. So this should be simple. I'm gonna do this. Where is the, here, self size. So what is this function doing? I'm getting the ASCII value of each character in the key. I'm summing it and I'm dividing it. I'm actually doing the modulo of the size. So we'll actually get a remainder that's gonna be from 0 to, it's gonna be from 0 to the limit that we provided, to the limit of the size. And because we here provided 10, so it's gonna be starting from 0 to 9. Okay, now how do we insert this? Self key value. First of all, I need an index. So it's gonna be self hash function of the key. So what happens here? Let me just open this. So let's say I provided, let's move here back. Let's say I provided a key and I get a value of it. So I get an index. Let's say the index is here. It's 1. I need to see if I have collisions. If not, then I can. Okay, so no, sorry. So if there's nothing here, I'm just gonna use the syntax and I'm gonna create a new node and it's gonna be key and value. But if we have something, what should I do here? So if I have something, let me just turn this on. If I have already an element here, what I'm gonna do, I'm gonna set this element's next to be my new node that I created. So what do I have? I'm getting the current node, and while the current node exists, if I have the key of this current node, I can update the value, then I can return. But if the next is none, I'm breaking this and I'm wait, so if the next is none, I'm breaking this and I'm setting alright, so let me just turn this again. Let's say we are at index 0, and here we have foo. These are the keys. This is bar. And let's say I want another one here. So what I'm doing is I'm going I'm creating a while. So while is there, well, we have an element here. I'm saying, okay, this element next is this element. So as long as we have an element, I'm just saying, okay, as long as we have next, please set the current to next. And as long as we don't have next, we are breaking the loop. We are breaking the loop. And after we break the loop, I do this. Right, for now, the only thing I'm gonna need is inserting. I won't be needing deleting yet, inserting and displaying. So for I node in enumerate self table, print so while we have a current, we're gonna print, we're gonna set the current to be current next, and then I'm gonna print none if we don't have any. But here, so what I'm gonna print here, save this. Let's create a hash table. Let's insert a couple of elements. Let's also insert some collision elements. What? Yes. And now I can print hash table contents, hash table display. Okay. I don't know if this is gonna work. Let me just divide this, split vertically. Yeah, in case I'm gonna need to Python 3 hash table. If it works first time around, no, of course it doesn't work. Hash table has no attribute display. My bad. My bad, my bad, my bad. This needs to go here, and I need to do the same for each line. There's not probably a shortcut in Neovim, but I have no time to look for short. Nice. Nice, 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 nice. This is really good actually. This is the hash table. This is basically the hash table created right here. Wow, nice. Okay, I'm gonna end it here. 1 hour 40 minutes, quite a long time.